In exploring the X-ray spectrum of black hole or X-ray binaries, such as Cygnus X1, we noted that there are two major spectral components. The first of these features is related to the disk spectrum of X-ray binaries. Here we will explore the second major component. Astronomers have found that the best explanation for this component is a diffuse region of gas that emits via inverse Compton scattering. This region is often labelled the corona, but it is also sometimes called the hot inner flow. The component of the spectrum stretches out over a large fraction of the X-ray band, slowly increasing in brightness as it extends to higher photon frequencies or shorter and shorter wavelengths, before turning over and dropping off. Astronomers think that the emission we observe from this region is fed by the disk. Coronal photons are thought to originate from the accretion disk. This means that when photons escape the disk in the direction of the corona, they can interact with the electrons in the corona via inverse Compton scattering and gain energy while moving through the corona. This increase in photon energy can either be small or large. This means that the photons escaping the corona can have a wide range of energies, which results in the long, slowly increasing slope observed in this spectrum. We should also note that the electrons in the corona are slowed down slightly as they give up energy to the passing photons. The coronal spectrum component of the black hole spectrum is clearly visible in the X-ray band for X-ray binaries. Would this still be the case if the black hole was larger? We saw earlier in this module that the disk component of the spectrum is shifted to ultraviolet wavelengths for a supermassive black hole. Is the same true for the coronal component? The photons from the inner disk feed the corona, where they gain energy via inverse Compton scattering. Therefore, the temperature or wavelength of the inner disk photons will impact the temperature and wavelength we observe in the coronal component of the spectrum. Just as the temperature of the disk can be tied to the mass of the black hole, the corona can also be impacted by the mass of the black hole. For supermassive black holes, the disk emission is seen to peak in the ultraviolet. As such, the coronal component is shifted to longer X-ray wavelengths. However, if the supermassive black hole resides in a galaxy that is moving away from us, the coronal emission will be redshifted into the optical and ultraviolet wavebands. Now that we know what the emission from the corona looks like, what can this tell us about the structure around the black hole? There are a couple of different theories for the location of the corona. The first of these is the lamppost model, which suggests that the corona is a cloud of gas that sits at a certain height above and below the accretion disk, as if it were suspended on a pole or lamppost. The second is more of a sandwich model, in which the corona and the hot inner flow extend out above and below the accretion disk as well as towards the black hole. In this case, the disk and corona are in contact with one another. Given the current data that is available from black holes, we know what interactions are happening within the corona. Do we have a lamppost hanging out above the black hole accretion disk? Or are we wrapped up in bagels? As yet, this is still unclear. Astronomers are still working to answer this question.